first of all, to see how this is all going to work out. And the other thing is to pick up where we left off. We were working in section 14.1. Remember, we were doing double integrals, and we did many examples, of course, and we'll do a couple more, but just something else I wanted to show you, because I think we mentioned this briefly about the volume and how to calculate the volume using the definite integral. So let's be a little bit more precise about that. So consider the following. Okay, so we have some surface z equals f of x and y, and we'll say it casts a shadow onto the xy plane. Let's say the shadow looks like this. Okay, we'll call that region R. Next thing we want to do is, we want to take this region and we want to cut it up into n rectangular pieces. Okay. Now they don't all have to be the same width and length. That's nice. Remember from your calculus 2 days, they would refer to that as a regular partition. Okay. So maybe something like this. Okay. Next thing is, I'm going to highlight one of these rectangular regions. Say maybe this one right here. Okay. Now remember, like we usually say, that these are infinitesimally small, right? Infinitesimally tiny pieces. So what I'm going to do first is, I'm going to take this red region right here, and I'm going to put it over here. Make it a little bit bigger so we can see it. Remember, it's infinitesimally tiny, so its dimensions then should be these, okay? And so we say the area of this differential element of area, that's what we refer to it as, right? Differential element of area. And we would refer to that as dA, which is dx dy. And because the order of multiplication doesn't matter, we can certainly write like this, okay? Now, be mindful, there's an infinite amount of these things, theoretically, right? There's an infinite amount of these things inside this blue region. If we were to add those all together, sum them all up, you would actually have the area of this region. Now, we didn't set out to find that. Remember, we're trying to find the volume that's trapped between this surface and this blue region down here. But we're going to get something else out of it. We're going to actually find the area of this region. So if we sum up all of the areas of those differential elements, we should get as follows, right? Okay, we read this as the sum of all of the differential elements as they range over the region R. We typically write with a double integral, though, because we know that dA represents two differentials, the multiplication of it, that is dx and dy. So we can write like this, which is more the convention that we use. So this is the area of R. Okay? All right, now, to continue with our discussion now, what I'm going to do is, I'm going to take the 4 lines on this rectangle, and I'm going to project them up onto the surface. Okay? That's going to look like this. Okay? Now, it looks almost like for lack of better words, we'll say like a rectangular prism. Okay? And if we could find the length, the width, and the height of that thing, we would have an approximation to the volume of this rectangular prism. Okay? It's not perfect, right, because it's curved on the top, but because it's so infinitesimally thin, it can be estimated with a column. So here's what I'm going to do. I'm going to take any point inside this red rectangle. There's an infinite amount to choose from. I'm going to just take one. Its corresponding point on the surface would look like that. Okay, now why the subscripts? The subscripts right? Think about it as there's n rectangles inside before we actually do the sum as n goes to infinity. So this would be the ith rectangle, okay? So the volume of this, because it's so closely approximated by a rectangular prism, the volume of a rectangular prism is going to be the height times the area of the base, okay? So we'll say that the volume, the differential element of volume of this column is equal to now the height of it is going to be the z-coordinate of this black dot. The base, well, we found the area of the base, that was this expression right here. So multiplied by dA. Okay? Now sum all of those up, right? We imagine that there's an infinite amount, right? One column for each one of those rectangles that are in there. So there's n of them, and then we say we take the limit as n goes to infinity. That's the whole business with the Riemann sum. Okay? We say that the total volume is the sum of all of those elements as they range over the region R. Okay, so that's how you read this. But typically we would write like this. Okay? Don't lose sight of this, gang. This represents the volume of the solid that's trapped between the surface, z equals f of x and y. Notice the integrand here. And the region R, the shadow that it casts onto the xy plane. Now it might not be the entire shadow. Sometimes the problem may modify the shadow for us. In other words, we only want the amount of volume that's underneath this surface, but maybe over a little square region, or a little rectangular region, or a circular region, not necessarily this thing right here. Okay, but the convention is the same. Okay? Alright, so we'll stop this one, and we'll try some examples. We'll get some examples from